Example 5.3, happy and sad balls, starting on page 163 and continuing to 164. It says you have two balls of identical mass and size that behave very differently. When you drop the so-called sad ball, it thuds on the floor and does not bounce at all. When you drop the so-called happy ball from the same height, it bounces back to almost the same height from which it was dropped. The difference in the bouncing ability of the happy ball is due to its internal structure. It is made of a different material. You can hang each ball from a string of identical length and place a wooden board on its end directly below the support for each string. You pull each ball back to an equal height and release the balls one at a time. When each ball hits the board, which has the best chance of knocking the board over? The happy ball or the sad ball?
Sad.
So we're going to start with some sketches. This will be our initial condition here. I shall write initial. I. N-I.
Mr. Whalen, what's your guess?
I-A-L. Initial.
Is it happy?
So this is sort of a before part, and it's going towards the wall, and it's going to collide. Same thing here. This is the happy ball going towards the wall. It's going to collide. So we've got velocity of the sad ball initially. It's going to have a velocity. But since it's the same size ball at the same height, our velocity of our happy ball initially and the velocity of our sad ball initially are going to be the same. So we could just call, in each situation, they're moving at some initial velocity. That'll be important later when we can combine terms, because they're both going to have the same initial velocity. I should define that this is a x direction or an x plane, although I think you can sort of see that. And this is going to be our final condition. Or, oh boy. Yeah, I got a little crazy there. Fancy. Okay, and this is going to be my final condition. And the sad ball is just going to go thud and hit the block, and it's not going to bounce back. The happy ball is going to bounce back. So we've got velocity of our sad ball final. It's going to be equal to 0. And the velocity of the happy ball final is going to be equal to the initial velocity, but in the opposite direction. Because it said when you drop this happy ball, it bounces up to almost the same height. So we can assume that when it bounces, it returns with almost the same velocity. And for this case, we'll just say it is the same height and it is the same velocity. So in the first situation, we have the momentum of the sad ball initially in the x direction. And we'll use the fact that we can have an impulse. The impulse is going to be an impulse provided by the block onto that sad ball in the x direction. And depending on what that block provides as an impulse, we're going to get a momentum of the sad ball final in the x direction. It's going to look similar over here with the happy ball. We're going to have a momentum of the happy ball initially plus the impulse of the ball, or the board, I'm sorry. That's where it gets confusing. B for board. Board on happy ball in the x direction is going to be equal to the momentum of the happy ball final in the x direction. To do this problem, we're going to use something called impulse momentum bar charts to sort of show us situations. So we're just going to represent each of these things by a bar, since we're not given any numbers at all. So we could have a bar that represents the momentum of the sad ball initially in the x direction. Let's say it goes up that high. And in order for there to be no momentum at the end, because it's a sad ball, it just goes thud. It has no velocity, no momentum. So in this third area, there's going to be no chart or no bar chart. It's 0. In order to get from this high to 0, you have to have an impulse equal and opposite to that. So if you have this for your initial momentum, this is your impulse. You're going to end up with 0 for the momentum of the sad ball in the final momentum of the sad ball in the x direction. The happy ball has that same initial momentum, but it ends up going the same velocity in the opposite direction. So it has the same size bar, but in the opposite direction. The only way we can change momentum is with an impulse. So if we have a bar this big, and we end up with a bar this big would have canceled it out. So our impulse has to be at least this big, but bigger. It's got to be twice as big. So if you go back up and see how these were arranged, we have our momentum on the sad ball in the initially in the x direction, plus the impulse on the board, or the board on the sad ball in the x direction, equals the momentum of the sad ball final in the x direction. And we can write those in a more specific way, where it would be mass, that'd be mass of that ball, times that initial velocity. Remember, the sad ball and the happy ball are going to have the same initial velocity because it's the same ball dropped from the same height, the same mass and size of ball from the same height with the same length string. Plus that force of the board on that sad ball in the x direction multiplied by some change in time equals that mass of that ball times the final velocity of the sad ball. Since the sad ball just stops with a thud, that final velocity is 0 for our final momentum. That means this entire momentum ends up being 0 at the end. It doesn't matter what the mass is, it's not moving. So to get force by itself, I want to subtract mass times initial velocity of that sad ball from each side, where I would end up with force of that board on that sad ball in the x direction times a change in time equals negative mass initial velocity. And since we are trying to get force by itself, we're going to divide both these by change in time. So that would end up canceling. So the force of the board on the sad ball in the x direction is equal to the opposite of the mass of that sad ball, the initial velocity of that sad ball, over the change in time. Now if we do something similar with the happy ball, it's going to be mass of that ball, initial velocity of that ball, plus the force of that board on the happy ball in the x direction, times change in time. And that's going to be equal to the mass of the happy ball times the velocity, the initial velocity, but it's going to be going in the opposite direction because it bounced away. So I'm going to again want to try to get force by itself. So subtract mass times initial velocity, subtract mass times initial velocity. Cancels here. But then what happens here is now we've got two of the same term. 2 times mass, actually it would be a negative 2, times mass times initial velocity is equal to the force of the ball. Ah, darn it, it's force on the board on the happy ball in the x direction times a change in time. And we want force by itself, so again we'll divide by change in time. That cancels. So the force of on the ball, I did it again. The force of the board on the happy ball in the x direction is negative just because it's the opposite direction. 2 times the mass initial velocity change in time, while the sad ball is just mass velocity change in time. So the happy ball will, or the board, I should say, will exert twice the force on the happy ball as it will on the sad ball.